Okay, in this short screencast, what I want to do is just go over the 6 prepared problems that we were not able to complete while we were in the class. Just an FYI, and I also posted an announcement on Blackboard that the wikis, the 3 relevant wikis for carbonyl, carboxyl, and the condensation reactions, that is available on the left side panel. Just click on wiki and access whichever you want. It is available for the entire class, so you would be able to, you'll have to go through click by click. The file just became too big to be uploaded, so I just gave you access. So I want to go over the first prepared problem here. I am given an ester and I have a ketone, and realize it's going through a cyclization. So you have to think about what you have, where you want to go with that. Also realize that you don't have an ester. A good rule of thumb here would be whenever you have an ester, the O-methyl part of that's a good leaving group, because the corresponding conjugate acid is the alcohol, which is a mild acid. So what would happen if you treat this is similar to one of the problems that we did for fill in the blank, I believe. I think it was Jessica's problem. Yeah, I think it was that. But let's see what would happen if you treat it with sodium methoxide and you follow it with hydrolysis with hydronium ion. In that case, realize that between the two, the one that you have here is, let's call this A, let's call this B, let's call this C. C is not going to go through deprotonation. The reason being the ester is resonance stabilized. So it's a question between A and B, and A is more or A is less sterically demanding, which is why you're going to get a negative sign on A and O-methyl. So now that you have generated essentially a negative sign on the alpha carbon, essentially that's going to go attack at the carbonyl. Electrons are going to move. So if I number, let's put it 1, 2, 3, 4, 5, and 6. It's a 6-member ring that you're going to get. You have an O negative, you have an O methyl, that's carbon 1, this is 2, 3, 4, 5, 6. The new bond is really the 1,6 bond, that's the new bond. And you have a double bond O at carbon number 5. Now the electrons come back, the methoxide is going to leave, and you're going to end up with a diketone, much the same way as we saw in class. Now if you set the stage and if you treat this with LDA, which is a good base, and you treat that with methyl iodide, CH3I, hopefully you can see that one of these protons is going to get deprotonated, and that will that'll react with the methyl group, and it's going to give you an H, a methyl, a double bond O, and a double bond O, and then another round of LDA followed by methyl iodide is going to get rid of the second proton, and treatment with methyl iodide is going to give you your desired product. Okay, another problem here was that we start with benzene and we convert it into this aldehyde. Realize that the aldehyde here can be generated. This is of the kind, this is your alpha, this is your beta, so this is an alpha beta unsaturated system, and one way you know of accessing that is through the aldol. So the question is, what would happen if I were to add, let's say, an H and OH across that? So I'm just going to write that on the side so you can perhaps view that. This is my pH. That's my alpha, and this is beta. So this is the beta hydroxyaldol system. So perhaps you can see that if I cleave the bond here, essentially this is an aldol reaction on 1, 2, 3. 1, 2, only 2. So 2-phenyl ethanol is essentially what I have, and an aldol on that is going to give you the desired product. So the question is, how can we generate 2-phenyl ethanol from benzene? Realize it's an aldehyde, so you could get that from, perhaps if you had a terminal alcohol. And if you're thinking about a terminal alcohol, well, there's many ways actually to do that. You can, if you have some way of putting the double bond onto the benzene ring, you can just carry out a hydroboration to give you this particular alcohol. Alternatively, if you had perhaps an epoxide and you treat it with a Grignard reagent, the phenyl Grignard reagent, that also will do that. So let's try a couple things here. So I have benzene. I'm going to treat that with chlorine, FeCl3. That's going to give you chlorobenzene. Chlorobenzene can be treated with magnesium, dry ether, 0 degrees Celsius, and it's going to give you MgCl. So that's my Grignard reagent, and let's say I treat that with the epoxide. Now the nature of Grignard reagent is that it is negatively charged, so it's basic in nature. That means it's going to ring open from the least sterically active site, which in this case, by the way, is, it really doesn't matter because both of these are equivalent. So let's just show the attack, and that will give you the desired alcohol. That alcohol can then be subjected to, so of course there will be a hydrolysis step. So epoxide is the first step. Second step is you have to hydrolyze it. You'll have to treat it with something like PCC to give you the aldehyde, and then that will have to be subjected to aldol using a base, so 2 moles of that and a base. Let's just write 2x. I'm just writing that so that you know how to get there. Another alternative would be, if you, like I said, if you can generate this styrene and subject that to BH3THF and treat that with sodium hydroxide and H2O2, that too will give you the desired alcohol. The question is, how can you get that going? Well, you can treat that with CH3COCl, right, with AlCl3. So that will give you, through a Friedel-Crafts acylation, it will give you the ketone. Now that ketone can be reduced with the hydrogen palladium. So this is the second route that I'm showing you, and that will give you the ethyl group. Carry out an NBS reaction, and that will brominate at the benzylic site. So let me just write that. That will brominate the, yes. And this, when subjected to KOH, let's treat this with KOH so that it eliminates and gives you the desired styrene molecule. And that styrene, when subjected to hydroboration reaction conditions, will give you the alcohol that will be subjected to oxidation to give you PCC, to give you the aldehyde, and finally through an aldol, it's going to give you your desired aldehyde. And the last problem was that you were given an alcohol and it's supposed to be converted into this alcohol, which has a double bond at the beta position, beta gamma position here. So the first step is obviously to convert it into an aldehyde. So I used PCC for that, and the solvent can be CH2Cl2. So you get the aldehyde, and now if you subject that to treatment with sodium hydroxide, 2 moles of this to show you an aldol should give you, let's just draw that. That's my aldol. 1, 2, 3, 4. 4 carbon, right? So 1, 2, 3, 4. 1, 2, 3, 4. Oh, there's way too many. Let's get rid of that too. The alpha position is right here. So hopefully you can see 1, 2, 3. This is the aldehyde that you would get. And now if you treat this with Grignard reagent, and the Grignard reagent, since you need only 1 methyl, it's a secondary alcohol that you have, secondary alcohol right here. So if I treat it with methyl magnesium bromide followed by hydrolysis, it's going to react at the aldehyde level to generate the secondary alcohol, and that'll be your product.